going to go through several trig integrals, but also how to approach the different types of trig integrals. Obviously, we have the standard integrals to help us out. So we know that sine will go to minus cos. We know cos goes to sine. We know sec squared goes to tan. And okay, tan is not a standard one that's on the sheet, but if you remember, it's sine on cos, so minus the log of cos or the log of sec. So there's our basic ratios there. What happens if we've got either sine to the power of something or cosine to the power of something? Now, I'm just going to go through sine to the power of something. The technique is exactly the same for cos to the power of something because they're basically the same function, it's just there's a shift happening. So sine to the power of n. If they give you sine to the power of 1, of course that's just minus cos. Even sine squared now should be straightforward because we know sine squared is half of 1 minus cos 2x, and then that becomes half that side of x minus a half sine 2x. So we've seen both of those, well, several times now. Let's move it up a power. Sine cubed. How to integrate sine cubed? I'm going to rewrite it as sine x times sine squared x, because then I can use a trig identity and change the sine squared to 1 minus cos squared. I can now do a substitution, because if I let u equal cos x, du is minus sine x, and we end up with minus 1 minus u squared du, which is a third u cubed minus u, and subbing the u back in. So basically, if it is an odd power, you always factorise out the power of 1. Because if you factorise out the power of 1, you'll be left with that trig function, whether it be sine or cos, to an even power. The even power, well, let's say it's sine we're dealing with, we can always write as sine squared to some power. The sine squared we can always change to 1 minus cos squared, and then we can do our substitution, u equals cos x. So that's how we handle any odd power. Even power. Okay, sine to the power of 4, I'm going to rewrite it a bit differently. This time I'm not going to take the sine x out, because that's not going to help me. If I take the sine x out on that one, I'll be left with an odd power, won't I? And I can't write that as sine squared to the power of an integer. So it's not going to help me. So sine squared squared. So this time I use the trig identity that sine squared is a half of 1 minus cos 2x. But I'm squaring that, so my half becomes a quarter, and I've got 1 minus cos 2x all squared. That I can expand out. The 1 I can integrate. The cos I can integrate. The cos squared I've now got to change. The cos squared will become a half of 1 plus cos 4x. So tidying all that up, we've ended up with a quarter times the integral of 3 on 2 minus 2 cos 2x plus a half cos 4x, but everything there we can handle. So I get a quarter of 3 on 2x minus sine 2x plus an eighth of sine 4x. So if it is an even power, I will always write it as sine squared to some power, and the sine squared I will change into a half of 1 minus cos 2x. Now, depending on how big that power is, you might have to do that several times. Back to an odd, just to show you, okay, odd. So I'll pull out the sine x, it's sine squared squared. The sine squared I can write as 1 minus cos squared, u equals cos x, substitute in. See, the odd ones are much nicer than the even ones. And then we just add 1 to the power over the power. That's if we had either sine to the power of something, cos to the power of something. What happens if we've got both? We've got a mixture. Generally, we're used to going to do it by a straight substitution. Sine x or cos x, your choice, because you've got both of them there. I'll do it via a few examples here, rather than building up from 1, 2 and so on. Here I've got one where both of them are odd powers. Cos power 5 sine cubed. I'm going to rewrite the sine cubed as sine squared times sine. The sine squared I'll change to 1 minus cos squared. I can now do the substitution u equals cos x. I could have I could have done it a different way. I could have got the cos to the power of 5, rewritten that as cos times cos squared to the power of 2, change the cos squared to 1 minus sine squared, and done u equals sine x. Basically, I'm pulling out of the odd one a sine x or a cos x, because that's going to end up being my du. Everything else I can write in terms of the, in this case, cos x. If I'd done it the other way, sine x. Why did I choose it out of the sine rather than the cosine? All to do with the size of the power. I'm going to pull it out whatever the lowest power is. It's going to make my calculations a lot easier. Let's sub in, and voila, we get our answer. So okay, if they're both odd, it doesn't matter which one you choose for the u, but go for the higher power. So if the higher power is u, another way of saying is, it's the lower power, we're going to pull the single one out to become the du. One's odd, one's even. How do we deal with that one? Well, I'll always pull it out of the odd one. Because when I pull it out of the odd one, that leaves me with a square or an even power, and I can do my 1 minus cos squared or my 1 minus sine squared. So in this case, I've pulled it out of the cos cubed, leaving me with cos squared, which becomes 1 minus sine squared. I can now do the substitution. U equals sine x. Du then is cos x, and we can just substitute in. And there we go. So if one's odd and one's even, then it's always going to be the even one I'll have as u. So the odd one's the one that I end up rewriting. Well, that leaves this one. They're both even. Sine squared times cos squared. Okay. I could rewrite that as sine squared 1 minus sine squared. I then have sine to the power of something, and we saw before how we handle the sine to the powers. So you just change one of them to the other, because if it's even, you can always write it as sine squared or cos squared to the power of something. So you can always change it to the one function. Again, depending on how high those, I took the easy way out here and made them both the smallest even numbers that I could. Obviously the higher the power, the more work that's involved. And I've also done a little bit of a cheat there, because I knew those answers from when we worked them out before, and I've just substituted straight in. Well, remember, we've already worked out earlier what sine squared was and what sine to the power of 4 was, so I've just subbed it straight in to get my answer. Okay, so basically both even. Either change your sine squared to a 1 minus cos squared, or your cos squared to a 1 minus sine squared. It doesn't matter. But again, you'd go with the lower power, I guess, because that's going to give you a smaller expansion you'll eventually have to do. All right, so sine and cos. What about tan and cotan? Again, the technique's the same, because they are complementary, so one's just the other shifted a bit. So let's look at tan. Well, tan to the power of 1. Remember, we know that now to be 1 log minus the log of cos. Tan squared. Well, tan squared I can rewrite as sec squared minus 1, and sec squared integrates to be tan, and then the 1 integrates to be x. Okay. Tan cubed. I'm going to pull out the tan x. It leaves me with tan squared. You see, the derivative of tan is sec squared. So if I can change to get the sec squared, I can always do a substitution. So I pull out to make it, well, it looks like I've pulled out the tan x. I haven't. I've actually pulled out the tan squared and changed that. I'm always going to pull out the tan squared, because that'll give me the sec squared that I want. So sec squared minus 1, it then becomes tan x sec squared x. Well, there's derivative times function there, and then minus tan x, and we know the answer to that. If you don't see the derivative times the function, you could do, well, u equals tan x, so the u is sec squared. So we have u to u minus half of u squared, so half tan squared plus the log of cos x. Tan to the power of 4. Same again. So the advantage with tan is it's the same technique every single time. I'm pulling out the tan squared, changing it to sec squared minus 1, splitting it up into two new integrals. So this time I've got tan squared sec squared, which I can do via a substitution, and then I've got the integral of tan squared. So again, the higher the power is, you might have to do this process several times. So use tan x. Integral of tan squared, well, we worked that out before, so at the same time I've just plugged it in there. We get a third tan cubed minus tan x. Right. So tan, same technique every time. Sec or cosec? I'll do the secs. Integral of sec x. Now, I am not suggesting you do this, I am suggesting you memorize this. But this is where it comes from. I'm going to multiply top and bottom by sec plus tan. Seems an obvious thing to do, really, when you look at it. Isn't it? Because if you do that, look what happens to the top. Sec squared. Oh, hang on. Sec squared is the derivative of tan. Sec tan. Oh, hang on. Sec tan is the derivative of sec. You have derivative on function, so it's the log of sec plus tan. Personally, I just remember integral of sec is log of sec plus tan. Yeah? But that's the technique if you do have to derive it. Integral of sec squared. Well, that's a lot easier, isn't it? That's just tan x. Sec cubed then. Ugh. I've got some good news for you. This one's fun. It's the same as sec x times sec squared x. You know, I'm thinking, why on earth did you do that? You're not going to create derivative times function there. No, I'm not. But I can do it by parts. If u is sec x, du becomes sec tan, dv is sec squared, which means v is tan. So my integral becomes uv, sec x tan x, minus the integral of v du. Sec times tan squared. But the tan squared I can change to sec squared minus 1. So I now have sec x tan x minus the integral of sec cubed plus the integral of sec. Hang on, we know the integral of sec. That's the log of sec tan. Now that just leaves me with sec cubed. Oh, that was the question. Now I look at it not as a series of working, but I look at it as if it's an equation and say, well, I'll move that integral of sec cubed to the left-hand side. So 2 times the integral of sec cubed will be sec tan plus the log of sec plus tan. So 1 log of the integral of sec cubed is a half of sec tan plus a half of the log of sec plus tan. Isn't that one fun? So odd powers with sec. I've got some bad news for you. You're going to have to do it by parts. Even, I just pull out the sec squared, which leaves me with 1 plus tan squared, and I can just go u is tan x to u is sec squared. Oh, look at that, 1 plus u squared to u. So much quicker. So any even power, you'd rewrite it as sec squared times sec squared to some power. Second sec squared you change to the 1 plus tan squared, because sec squared then becomes the derivative of. Alright, hours of fun for the whole family.